Hello everyone. Today let's do some exercise by solving some congruence relationships. The source of this question is from American Invitational Mathematics Examination, aka AIME, 2021 problem number 13. Here comes the question. Find the least positive integer n for which 2 to the nth power plus 5 to the nth power minus n is a multiple of 1000. When we see this question, we know it asks us to solve an congruence relationship. Since 2 to the nth power plus 5 to the nth power minus n is multiple of 1000, is equivalent to 2 to the nth power plus 5 to the nth power minus n is congruent with 0 modulo 1000. And since 1000 can be written as 8 times 125, in which 8 and 125 are relative prime, then this congruence relationship can be written as the following two, with the first one modulus 8 and the second one modulus 125. And apparently n is larger than 3, since 2 to the nth power plus 5 to the nth power minus n is a number larger than 1000. So therefore, 2 to the nth power is a multiple of 8, and 5 to the nth power is a multiple of 125. Then, in the two relationships, the first one, 2 to the nth power, becomes 0, and in the second one, 5 to the nth power becomes 0. And then, the two relationships can be written as 5 to the nth power is congruent with n modulo 8, and 2 to the nth power is congruent with n modulo 125. Those are the two congruence relationships that we need to solve. Let's start with congruence number 1. 5 to the nth power is congruent with n modulo 8. We notice that this congruence relationship is not easy to handle, since 5 and 8 do not have a direct relationship. So instead of modulus 8, let's start with modulus 2 first. And this becomes much easier, since 5 to the nth power becomes 1 in the relationship. And that means m can be written as 2 times n0 plus 1. Now let's work on modulus 8. First of all, in this relationship, n is replaced with 2 times n0 plus 1. And 5 squared can be written as 25. Since 25 is congruent with 1 modulo 8, the left side becomes 5 times 1, and 5 minus 1 becomes 4. In this relationship, both sides will be divided by 2, and the modulus 8 will be divided by 2 too. And the relationship becomes 2 is congruent with n0 modulo 4, which means n0 can be written as 4 times n1 minus 2. Then that leads to n equals 8 times n1 minus 3. From here, we have already solved the first congruence relationship. Now let's move on to the next one. Congruence number 2. 2 to the nth power is congruent with n modulus 125. Similar to what we did before, let's start with modulus 5 first, instead of modulo 125. In this relationship, n is replaced with 8 times n1 minus 3. Both sides are multiplied by 8, and 2 to the 8th power is equal to 256, which is congruent with 1 modulo 5. 8 times 8 is 64, 8 times 3 is 24. 64 becomes minus 1, and minus 24 becomes 1 in the congruence relationship, which leads to n1 is congruent with 0 modulo 5, which means n1 equals 5 times n2, and therefore n can be written as 40 times n2 minus 3. Now let's move one step forward to work on modulo 25. In this relationship, n is replaced with 40 times n2 minus 3. Both sides are multiplied by 8. We note that the left side has 2 to the 40th power. This makes us think of Euler's theorem. In this theorem, it states a to the phi nth power is congruent with 1 modulo n if a and n are relative prime. Here, phi n is Euler's tangent function, which counts the positive integers up to a given integer n that are relatively prime to n. For example, for the number 25, there are a total of 5 numbers smaller or equal to 25 that are not coprime with 25. Then that means phi 25 equals 25 minus 5 equals 20. If we let a be 2, that means 2 to the 20th power is congruent with 1 modulo 25. This is definitely something we can make use of. Then the left side can be written as 2 to the 20th power, then to the 2 n2th power, and it becomes 1. A times 40 equals 320 becomes minus 5. A times 3 becomes 24. Minus 24 becomes plus 1 in the congruence relationship. And both sides are subtracted by 1 and divided by 5. The modulo 25 will be divided by 5 too, which leads to n2 is congruent with 0 modulo 5, which means n2 can be written as 5 times n3. Then n can be written as 200 times n3 minus 3. As a last step, let's work on modulus 125. In the relationship, n is replaced with 200 times n3 minus 3. Again, both sides are multiplied by 8. And we also apply Euler's theorem here. And phi 125 equals 100. Then the left side can be written as 2 to the 100th power, then to the 2 times n3's power, which becomes 1. The right side, 8 times 200 becomes 600, becomes minus 25. And 8 times 3 becomes minus 24. Both sides are added by 24, then divided by 25. The modulus 125 will be divided by 25 too, which leads to n3 is congruent with minus 1 modulo 5, which means n3 can be written as 5 times n4 minus 1. Then, eventually, n could be written as 1000 times n4 minus 203. Then, the minimum value of n can be achieved when n4 is 1, and therefore n is equal to 1000 minus 203, which is 797. So 797 is the minimum value of n that we can find, so that 2 to the nth power plus 5 to the nth power minus n is a multiple of 1000. This problem gets resolved. As a practice, please find the least positive integer n for which 3 to the nth power plus n is a multiple of 100. Thank you.